Okay, so in the last few minutes, I want to sort of tell you how the slip model actually helps us understand the way Mark Raibert built his hopping controllers, which came first, actually. Mark Raibert built his hopping controllers well before people were talking about slip. In fact, you could say that the slip models sort of came from people trying to understand how the heck Mark Raibert's controllers worked, okay? So you remember the hopping videos I showed you before. The first robot that Mark built was this hopping robot here that had weights out on the edges, okay, to make the inertia of the body large. It had two actuators. It has a piston in the leg and then a torque actuator, so that's a pneumatic actuator in the length of the leg, so that the pneumatics could act as like a spring, and then you could inject energy if you like. And then it had a hydraulic torque actuator at the hip. Okay, and you actually on day one simulated that controller, right? Had this simple model hopping around in MATLAB, right? And that had my approximation of his controller. I wanted to make it time invariant, but other than that, it's almost exactly his controller. And it turns out his controller, I'm not supposed to show that yet, you know. His controller is surprisingly simple, right? So all this talk I've been doing about, which I very much believe in, about optimization and everything like that, he didn't do any of that, right? He uses physical intuition, and in general has been a proponent of intuitive control, and came out with something that worked very nicely to stabilize the simple hopping machines, okay? So I'll just sketch the ideas behind that. So he wrote his algorithm in 3 parts, okay? The first one was a controller that just controlled hopping height. The second controller controlled only body attitude, pitch of the body. And the third one controlled forward speed of the robot. Okay. The hopping height controller was sort of painfully simple. So my predisposition, if I were to build a hopping height controller for a robot like this, is I'd start modeling the basic impact dynamics of the ground, some of the pneumatics in the leg, come up with an approximate model. We can do all these things, and that recipe will work for more complicated machines. But for this one, Mark in his lab said, you know what? If I hold the pneumatic pressure constant, every time the robot goes down, it's going to lose a little energy in the cylinder and start hopping slower. But if every time the foot hits the ground, I just put a constant amount of energy in, just every time the foot hits the ground, then it's going to go back up, and it'll find some stable hopping height for any constant energy in. And if I turn that number up, it hops higher. And if I turn that number down, it hops lower. So that's good enough, So and that was brilliant. I mean, so basically, he had a simple dial that would control the hopping height of the robot. And if the foot's moving around, yeah, that changes the map a little bit, but it's still monotonically. The hopping height will still be monotonically related to where I turn the dial. So that's my hopping height controller. It's a dial like this. If it looks like the robot's too low, I'll turn it up, right? So the key observation was that the hopping apex height, let's say, related to input command, which was a pressure. And that was it. So, and then people, so Dan Kodacek, for instance, went back and analyzed simple models of that hopping robot and showed for reasonable models of the leg spring and reasonable inputs and everything like this. And it was, in fact, a return map that we could understand to have a stable fixed point, right? But you know, Mark knew that, and he just turned the dial, and that was his brilliance. Okay, same thing for body attitude. So how do you control the pitch of your robot? Well, that's tough, right? So like when you're in the air, you can't control your total angular momentum, but you can sort of move things relative to each other. That's hard, right? What I'm going to do is I'm going to put the inertia of the body out on the edges of the rod here, so that when I'm moving around in the air, my leg is pretty light relative to my body. So basically, I'll move my leg around to do what it needs to do in the air, and the body's not going to move very much, right? And if it's moving a lot, I'll put a little more mass up there, right? Simple. So that allows me to decompose the controller. And then at the moment when the foot's on the ground, then now a torque at the hip, you have sort of you have the mass of the earth on the other end, right? So, so you can now impart a torque on your body during the stance phase. And he just did a position control of the body during the stance phase and left it alone in the air, right? And that was enough to do body attitude control. Although when I've played with the controller, and I think when people afterwards have played with the controller, this is the most sensitive part. This is the hardest part to tune in, right? And of course, when I'm doing position control of the body during stance, that's also affecting the leg angle, but we'll just ignore that. Yeah, that's and then the forward speed is maybe the most interesting. And you'll guess the theme here, but Mark basically observed that at steady state, if I put myself down at a certain touchdown angle, and this, remember, predated the slip model, for a certain touchdown angle, there was a magic touchdown angle where I'd come off symmetric. Okay, where I'd come off at the same angle here as I did here. Okay, there was a Okay, so he did some work to figure out what that touchdown angle looked like with a simple model. Again, before slip, but the slip can help you understand this too. And then he observed that if I put my foot a little bit in front of that, what happens? I slow down, right? Because I come out, you know, I come in and I come out less, more vertical. So I'm trading some of my energy into the air. And if I want to go faster, I put my foot down a little bit before that magic point, and I'll come out faster. So my speed controller was a position control on the ground for foot placement, which mapped to a touchdown angle command at the hip, so you can move your swing leg like this. Okay? Very simple, very robust controller that worked on the real hardware, way more dynamic at the time than anything else out there. Right? So, and let me show you some of the things he did with it. So from this, I mean, you can see my implementation of the controller there, but so he went on to build two-legged things that could hop over and do flips I showed you before. He went on to build quadrupeds. Now you can see by the resolution of the video, this was a long time ago, yeah? Right? This was the quadrupeds. He's got a great paper that's called Running on Four Legs as Though They Were One, okay? Where it's told the story of taking that simple monopod hopping idea and making the virtual leg spring, which was kind of like this picture I've been showing you with the slip model, and using that to program the quadruped and the biped. And this thing could do a lot of the quadruped gaits dynamically. It's very simple. It's not doing foot placement, right? So if there was stepping stones it had to run over, That's tough. There was actually Jessica Hodgins who did some work on trying to do foot placement in that framework for simple things. But this is just a very simple, make the robot the right way and you can do simple control idea. And really, that has been the story that has continued to work. This is Big Dog. So Mark Raibert left academia, started a company, Boston Dynamics. They did simulation for 10 years. And then he came back, and I was in the leg lab the day that he came back and he said, is anybody using that treadmill over there? I'm going to start building robots again. And a few years later here, there's Big Dog walking around. And the story that they tell about the way the controller works here, I think there's massive amounts of very talented engineering in here. But basically, the idea is the same. The body is heavy. The legs are light. The torque, the power in the actuators is sufficient that if you kick it, it can always put its leg out where it needs to get this basic speed controller in 3D working. And that was enough to get these guys walking around and sort of, I'd say for the first time, making legged robots look like a real thing that would really work in the world. It's just awesome. And then from there, they went off and they've just, the story is really, they've got slightly different simple models now. They've got really good state estimation, really good control of their actuators. They've engineered the heck out of it, but the control story is still surprisingly similar to the story that they tell about the hoppers. Okay, so I think this is where we're at right now. And I'll just end by saying that actually, so what we're working on in our group is sort of what I hope to be, and other people are working on too, is sort of the next. You guys aren't going to listen to me if I put that on. So let's say you do want to do that with stepping stones or with more complicated contact. If you wanted to build an American Ninja Warrior robot or something like this, right? Then the tools we've been talking about will still work, right? So our version of trying to make Atlas work, we did trajectory optimization. And we asked for a periodic solution to Atlas running and did a lot of work to try to write that down in a formulation that was simple enough that it could be run quickly and use a simple, important way, some tricks to write down the problem so that it had less local minima and the like. But now we can have Atlas running. And our same code didn't require assumptions about the robot or whatever, can do the same thing for little dogs. So for better, for worse, the tools that we're using with trajectory optimization and then stabilization with the quadratic programming stabilization that Scott told you about can solve these harder problems, okay? But they're not nearly as simple, nor robust yet, really, as the controllers Raibert showed. They do generalize, so we can make Atlas do all kinds of crazy things, and I hope you'll see the real robot doing that soon. Good. So we'll see you here on Thursday, and perhaps tonight at the review session.